Okay, good evening, this is Mr. Steele. I'm here making this video and wasting my time because I was so appalled by the quality of the homework and how little mastery I saw in the graphs of the rational functions on worksheet number 1, handout number 1 from last week that I figured it must be that I need to have another example. So here I am. Basically I'm going to go through at least one example. If the video works great, this will go up there. If it doesn't, oh well, I'm not going to try it a second time. So basically the purpose here is for me to go through a full example explaining everything as best I can and then graphing it as well so that you kind of see everything. So to start off, kind of show you where we're going, you want to graph a rational function and complete the analysis just like you'll be asked to do on the test on this grid. So it's not perfect, but this is the best that I can offer you as far as like an extra resource. So here we go. I get the mouse out of the way. So what we're going to do is we're going to graph a rational function, and the function that we're going to be graphing is going to be this one. Y equals x squared plus 3x minus 10 all over x squared minus 4. So I don't remember if we've done this one in class or not, but even so I think it's probably still a good thing to do. So starting off, in order to graph this we have to analyze it and find some specific pieces of information, and each one of those steps or processes that you need to use in order to find that information, the pieces listed here, is in your notes, but at the same time you still kind of go over it verbally. So starting off, the first thing that we want to find is the EBA, so that's the end behavior asymptote, and that basically is going to tell us what happens as this function goes towards really big values, in particular positive infinity and negative infinity. So that's our first place that we're going to check. So in order to find the EBA, I'll use some colors here as best I can. So in order to find the EBA, we're basically going to divide. That's the whole process. So in this case we've got to divide x squared plus 3x minus 10 by x squared minus 4. So again, there are shortcuts here, and we've used them before, based on if the degrees match on top and bottom, such stuff like that. But at the same time, let me start here. So when in doubt, we can do the full thing. So if we're dividing this out, we have to see how many times does x squared go into x squared. The answer is it goes in 1 time. So x squared times 1 is x squared. Negative 4 times 1 is negative 4. Draw the line, change the signs. We're going to get a 0 there. We'll have 3x minus 6 as our remainder there. Now we ask how many times does x squared go into 3x, and it doesn't. So in fact we've actually found our EBA right here. This will be our EBA, 1. But of course we want to write our EBA as a function so that we can graph it onto our graph as we get started. So in fact our EBA is not just going to be 1, but y equals 1. So as you plug in really big numbers, like positive all the way up to positive infinity or all the way down to negative infinity, you're going to get numbers closer and closer, never officially touching, but getting really, really close to 1. So to graph that EBA of y equals 1, we can go onto our grid, and at y equals 1, which is right here, we can graph a horizontal dashed line. Again, I graph it in green, not because we're going to cross it today in this example necessarily, but because there are situations where we do end up crossing that vertical asymptote, or that horizontal EBA asymptote. And so there we go. We've got our EBA down. So next thing we have to do is we have to check if there are any holes or point discontinuities. The way we need to do that is we need to actually do the factoring and simplifying. So we need to see if this rational function can be broken up in such a way that some factor might go away. So to do that, I'm just going to do a little bit of factoring. So the top part, if I look at x squared plus 3x minus 10, and I'm going to pull out a different color here, so I'm going to do the whole. So we're thinking about what things are going to cancel. If I look at that top part, I can diamond factor it. So what two numbers multiply negative 10 add up to 3. However you like to do the diamond, you're going to get that this factors into x plus 5. I check, yes. X minus 2 all over x plus 2, x minus 2, with that denominator factoring based on the denominator there being a difference of squares. So right here, we've got kind of everything set up. And what you probably notice is that we actually get a little bit of cancellation here. Like x minus 2 and x minus 2, they're on top and bottom, so they do make a 1. They do, in effect, quote-unquote cancel. And so that means that we actually have a possibility for a hole. We actually have a place that if we were to plug in the specific value here, in particular it'd be 2, we'd end up with 0 over 0 in our original function. And that would be bad. Like, we can't have that. So what we need to do then is we need to now go, okay, so my whole, the factor that canceled is x minus 2. If I set that equal to 0, I'm going to get that x equals 2. Well, that tells me that the x coordinate of my whole is going to be 2. And so then what I need to do is I need to look at the new function that's left over after we pull out that, after we make a 1 with that original factor, and see where would that point have been. Like if we plugged in 2 into the new canceled out function, what would that value be? It won't actually be on the graph, but it will look like it is. So that my new function is x plus 5 over x plus 2. And so now if I plug in x equals 2 into there, I'll have 2 plus 5 over 2 plus 2 is going to be 7 over 4, and so there will be my y value, 7 over 4, or 1 3/4. And so now we have the whole, and on our graph, even though it won't be totally precise, we can go and actually plot that point. So 2 and 7/4, so 2, that'll be 1 3/4. That means we're going to have a whole right about there. So I mark it with an open dot. And again, even though it's kind of hard to tell, it is blue just like the other one. Okay, now that we've got the EBA in the whole, our next step is to start looking at the other pieces, and in particular I'm going to look at the vertical asymptotes. And now it's important to realize that for everything from the whole on downward, we're going to actually use not our original function, which is kind of full and not as factored. We're going to use the simplified new function right here. So this is going to be our new guy that we're going to look at everything with. So like I might even throw that off to the side. It's going to be x plus 5 over x plus 2 that we actually look at the rest of the way. So just something to keep in mind. So next I said we're going to look at the VA. The vertical asymptote comes from, or is found, when the denominator is set equal to 0. So it's like whatever this stuff is under, we basically set that equal to 0. So it's the Chuck Norris piece. It's only Chuck Norris can divide by 0. Everyone else has to have vertical asymptotes. So to do that, basically we look at our new function, x plus 5 over x plus 2. Our denominator is just x plus 2. So when that's equal to 0, we get that x equals negative 2. So we're going to have a vertical asymptote, a single one, at x equals negative 2. So notice that if we'd gone and used the original function, we would have had a vertical asymptote also at positive 2, but that's not true. We said positive 2 is a whole, so that does not have a VA. And so there we go, we've got a third piece of information. To graph it, we basically just have to draw a vertical line there. So x is equal to negative 2 right here. So I can draw a red vertical line that we shall never, ever, ever cross, ever, 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 under no circumstances. And there we go. We've kind of got the starting setup for our rational function. So VA is down. Next, let's look at the zeros. So zeros follow the vertical asymptotes because you're doing the same thing, just in a different spot. Like basically, a function will be equal to 0 if its numerator is equal to 0. And so in this case, we've got to look at the top equal to 0. So in this case, in our new function, our top is x plus 5. So when x plus 5 equals 0, that leaves x equal to negative 5. Now we don't write x equals negative 5 like it's a solution to a function, like we're trying to write it as a 0, as an ordered pair. So to do that, we write it as x comma 0. In this case, it'll be negative 5 comma 0. So they always look like number comma 0. And so once again, now that we've got it kind of written down, we can actually go plot it. So negative 2, negative 3, negative 4, negative 5. So there is our 0, plotted in purple. And so we've got a point over on that side. So next piece, the y-intercept. Let me grab a different color pen here for that one. I'll use orange, what the heck. So for the y-intercept, it's easy, it's the same way as before. You basically just have to plug in x equals 0. Because if you think about it, the y-intercept is going to be on the y-axis, and every point on the y-axis looks like 0 comma some number. So we've just got to put the 0 in for x and find out what y is. So again, we can put it into our new function, x plus 5 over x plus 2. If I do that, I'm going to get 0 plus 5, or 0 plus 2. That's going to be 5 over 2, or 2.5. Like either way would work. For this, I'm going to write it as 0 comma 5 over 2. But we know that's the same thing as 2.5. And so now I can go and throw it up over here by just plotting the point. So 0 comma 2.5 is right up there. And so now we've got the y-intercept in. So basically our entire function is finished here. The only thing we have to do now is actually plot, like kind of a representation of the rest of the points. So like where would the rest of the shape go? And the trick for plotting the rest of the points is first that you have to have one on each side of a vertical asymptote. Like you have to have at least one. More is better, but at least having one you can follow the tricks. And so in this case, if we look at our VA, we do in fact have a point on each side. We've got our 0 on the left side of it, and on the right side we have the y-intercept as well as a hole. That'll give us some guiding shapes to it. And so in fact we won't need to find any points this time, although we could to be more precise. And the way we do that obviously is to pick a number that's 1 away from the vertical asymptote because it usually makes it nice. But that's beside the point. What we can do though that always works is we can hug the asymptotes. So basically those asymptotes give us an idea for the behavior of the function at the extreme places. So if we kind of get really close to them, like at extreme places, like say over here or really close to the vertical asymptote, we can use them to kind of guide our shape. So if you watch kind of what I do, as it gets really close to negative infinity, it's going to get really close to that EBA. So if I follow it through, I can do that. So I start at the EBA and start to come down. Then it's going to get really close to the vertical asymptote as we get really close to -2. And so there we go. There's the left-hand side of our shape. On the right side, we do the same thing. So notice it's all up here. If we hug the asymptote, it's going to get really close there. Let's come down and through the point. Now at the hole, it does fit into the shape, but we don't actually go through it. So we're going to just kind of skip it, and then it gets really close to the EBA as we get towards infinity. And so there we go. There's our shape. I don't know if I can make it look a little bit better. Well, there we go. So we had our EBA, which we found by division. We had our hole, which we found by simplifying, and then just kind of canceling stuff out and seeing where that point would be in our new function. We have a vertical asymptote we found by setting the bottom equal to 0. We have a 0 that we found by setting the top equal to 0. And then we had the y-intercept we found by plugging in 0. We didn't have to find any additional points because we had at least one on each side of the vertical asymptote. And so there we go. We get our shape, and it looks like it's a pretty general one. So there you go. There's a pretty solid example of a rational function that's graphed with all the pieces. Hopefully that's been helpful.